how are things going so far? Is there anything that we've covered in the last session that you would like me to go back over? Any lingering questions from before? All right, so we'll keep going then where we stopped. This time we just started talking about the R subdirectory in R packages. This is where all of your R code lives. Just in a bunch of .r scripts, which you can essentially arrange however you like. Talked about a few things that should be remembered about the code in that subdirectory. A few more things. You shouldn't use code that creates side effects outside of functions. So, for example, if you want to plot something, especially if you're writing a package, you should create a plot function that does that. So don't include code in your package that just plots something and expect it to be plotted like when a user loads a package. That's kind of rude if someone goes to load up a package and it just starts plotting things. So don't use code that creates side effects on their own. Put those inside functions so that the user can just do that when they want to. In general, you shouldn't try to change the user's global environment, working directory options, or try to read or write files or communicate over the internet without the user's permission. And so all of these parts are just sort of being a good programming citizen. So we've all used our packages, and we like it when they behave nicely and do what we expect them to do. It's not very nice if a package goes and does something you don't expect it to, or starts plotting things or writing files that you don't know about, and then doesn't clean them up or things like that. You don't want to have a package just suddenly say that, oh, you don't want to suddenly find out that you don't have any hard drive space anymore because your package has been writing huge files without deleting them or anything like that. There are specific ways to create temporary files or temporary directories in R. If you do need to do that, might as well show you that real quick. So if you do find yourself like needing to find a place to write, say, a log file or something like that, or creating any sort of temporary file, well, first of all, again, that's something that should happen within a function, so that the user knows that it's going to happen, or at least can control when it happens. Let's see. But there are functions that let you create a temporary file or get access to a temporary directory if you happen to need those things. So use the R's built-in temp file and temp dir functions if you need to do those things. These will find an appropriate place on the operating system to write a temporary file and make sure it gets cleaned up and deleted after the user is done with their R session, so that these things don't happen. So and additionally, so don't change the user's global environment or working directory without them knowing. So when I go to load a file or like find a file in R, it's nice that I can assume I'm actually in the working directory that I set that I was in earlier. So if you need to like load a file, it's not the best idea to actually change the directory. Just use the full file path or something like that. One useful function to be aware of for that, there's a few functions. This one's part of the base package. There's a few functions in R that can turn file paths into their full file path forms in a cross-platform way. So, for example, if you want the user to be able to just use a relative directory, say file.txt that's in the current working directory, and you want to get the full file path to that, then you can use this normalized path function to get the full path to that file and make sure that works on all operating systems. Yeah, and then the other thing to know is that all of the R code in this folder will be evaluated in the order that they actually appear in the R scripts. So our scripts will be evaluated in alphabetical order. So if you have a file called AAA, that'll be evaluated first. If you have a file called ZZZ, that'll be last, and so forth. And then, of course, the scripts will just be evaluated in the order that they're written. For most code, this doesn't make any difference because R is a lazy language, so all your arguments and things and functions like that are evaluated lazily, so you don't actually need an object to exist before you can refer to it. So for most things, for most functions, that's perfectly fine, and it doesn't matter what order those get evaluated in. For a few cases, this does matter. For S4 classes specifically, the class must be defined before you can define methods for it. So if you're writing S4 classes and methods, then the order of evaluation does matter, because you need to actually define the class first before you can use it. Question?
So why is it only S4? Why is it not S3?
Because S3 essentially, S3 is a much simpler system. The method dispatch in S3 is basically just based on the naming scheme, so plot.dataframe or plot.formula, the plot formulas. So everything in S3 is fairly simple and basically behaves exactly like normal functions. To find the S3 method is basically following this naming scheme, and you can create an S3 method for a class that may not even exist yet, and things will work out fine as long as you follow that naming scheme. It's also made easier in S3 because all of the methods are single dispatch, so plot you can only change the behavior depending on the first argument that you give to it. S4 adds a lot more complexity and formality since and so because you have and we saw another example is the inheritance in S3. That just depends on basically the order of this class character vector attribute, whereas in S4 it's actually a built-in part of the class. So with S4, when you're defining S4 methods and S4 classes that inherit from other S4 classes, all of that actually gets defined in the background as some sort of side effect. The same is not true with S3. There's very little actual side effects that are happening behind the scenes with S3. In S4, pretty much all of this is side effects that happens behind the scenes. When you call set class behind the scenes, R is doing something to make sure that S4 class exists in some place, and it is aware what classes that inherits from. So all of that requires. So basically, if you end up writing an S4 method, how that works will depend on the definition of that class. So you need that class definition available, and so forth. Yeah.
So if you are creating an S4 class and writing methods, then you should name them in alphabetical, or you should name the class in such a way that alphabetically before the methods.
So there's a few different ways to take care of that. So for one, if in general, if you have S4 classes and methods in the same R script, you can just put them in the order that you want them to appear. So anything that's in the same R script in the same .r file, those will just be evaluated in the order that you wrote them in. Anything that is separated between different files, either you can just use a naming scheme to make sure those are in the correct alphabetical order, or you can use the collate field in the description file. So in this description file, I don't have it for this package because this one is relatively simple. Go ahead and pull up a package that uses collate. So this is the description file for one of my packages called matter. It has a bunch of S4 classes with different subclasses in different files. I didn't want to name them like A, B, C or something like that. So you can use, if you have a situation like that, you can use this collate field in the description, and then you just list all of the R files in that subdirectory in the order that you want them to be evaluated. So here, for example, you can see I have all of my generic functions in one script, and all of those generics are going to be created first, and then the rest of these are essentially in the order of the parent classes are being defined first, and then the child classes, and so forth. And when you use a collate field like this, you do have to list all of the R scripts in that file. So even the ones where the order of evaluation may not matter, you have to include all of them in this list somewhere. And they're not divided by commas or anything. It's just a list with space separated by spaces. Let's see, so we can take a look at the R scripts in this example package, this ProDXB package. In the R subdirectory here, I just have 3 files. I just have them separated into the S3 classes. So these look just like, the classes and functions that we were using earlier. You see some additional code comments, and we'll talk about that in just a moment. Here's all of the S4, and these are just written in the order that I want them evaluated. And then I'll talk about what this is in a little bit. Okay, so that's the R code in the R folder. The next directory we're going to talk about is the man subdirectory. So this directory includes all of the documentation for your package, as well as all of the R objects in it, including functions, methods, class definitions, and data sets that are exported to the user. You don't have to document things that no one's going to see. It is written in .rd files, which are based on LaTeX. If you're not familiar with LaTeX, it's a markup language for authoring documents. It's kind of similar to Markdown or HTML. And so it's used a lot for scientific writing. And so our documentation.rd files are based on essentially a dialect of LaTeX. So if you don't already know how to write LaTeX, then you should have no problem writing our documentation by hand. It's not that hard. But there's another useful way of writing our documentation using the roxygen system. So roxygen 2 is this package that allows us to keep our documentation with our code by just writing structured code comments, and then roxygen will generate the .rd documentation for us from these structured code comments. And this can be really useful for keeping together the documentation with the code itself. So here, for example, is some documentation for a particular function. This is for that protexp constructor function. And so remember this constructor, it returns an object of class protexp, but itself it's just a function. So we're going to document it like a function, and the way we do that with roxygen 2 is in these code comments. And to distinguish roxygen comments from just ordinary code comments you might have in the middle of your code, it uses both the hash that you normally use for our code comments, plus followed by an apostrophe. So roxygen 2 comments have this little apostrophe after them to distinguish them from regular code comments. So fairly simple. The first couple lines are, the first line here is just going to be the name of the documentation page for this particular function, and then followed by a description of what the function actually does. And you can see I'm actually using a little bit of LaTeX code in here, and that'll turn into LaTeX in the final R documentation. But for most things, I'm using this @ sign for different roxygen 2 directives. So for example, when we document a function, we need to document all of the arguments all of that function's formal arguments. And here we're doing that by using this @param directive. So for each of these arguments, I just have @param, the name of the argument, and then a description of what that parameter does. Here I'm using @return to describe what kind of object is being returned. And then here, this @export. This export directive, this is for the namespace. So I'm saying that I want users to be able to see and use this prot.exp function. Because remember, by default, all of the code in your in this R subdirectory, the user isn't necessarily going to see all of it. You might have a bunch of helper functions that people don't care about or won't need to use. So there's not necessarily a need to document all of them or export all of them. So here I'm using this export directive, and that'll be used to generate the namespace file that will say, I want this function to actually be exported to the user. I want the user to be able to use this function. So this is just a few examples of how you would document a function. So just the first few are a couple lines giving the title of the documentation page, a description of what the function does. For functions, we need to describe each of the arguments with these @param directives. We need an @return that will describe what is actually returned. And then if this is a function we want to export, we need @export.
So
Yes?
This only gives you like documentation. This doesn't actually change anything about the function itself. So like that you wrote that the log2 is true or false. It doesn't do validity.
Exactly. So all of this is purely documentation, all of these are actual comments. So none of this can be evaluated anyway. This will all just be used to generate documentation. It changes nothing about the function itself. The only one that actually ends up being meaningful in terms of how your package is loaded and how you can use functions is the export directive. This one will change the behavior in that it changes whether the user can actually see and use that function or not. The rest of this is purely documentation. The export is for the namespace that will define whether the user can see and use that function.
Is export kind of like source in that way?
So source is an R function that is used to parse and load R code from an R script. Export here is being used as a roxygen2 code comment directive, so that when we run roxygen2 to generate the documentation and namespace file, this function will end up in that namespace. So this is something that is solely used if you're creating an R package and using roxygen2 to do the documentation for it. So this is how you would write this documentation in roxygen2, and what that ends up looking like after we run roxygen on it, which we'll see how to do in a moment. This is what the actual documentation page for this actually ends up looking like. And we can see at the beginning there's a comment saying generated by roxygen. Roxygen2, do not edit by hand. Then it also tells the R script file where the documentation can be found. And so you can see if you've used any LaTeX at all, this is should look fairly familiar to you. There's just LaTeX macros and directives. So here, all of my all of those @param directives turned into items in this arguments list, and so forth. So this is something that you could write by hand if you want, if you're familiar with writing LaTeX, but is also really useful to instead have it as part of the code comments directly with the function itself. Because then when you go and change the function, you change the arguments, you need to go and update the the documentation to correspond with any of those changes, and it's a lot easier to do that if the documentation is right next to the code itself.
So is there a way to get that documentation to look like that help function, or is that like when you do the thing?
So when you actually install the package, so I already have it installed. So when you have the package installed and loaded, then all of that documentation is accessible via the normal help pages. So here, for example, so if I want to see what that documentation actually looks like for a user, I can pull that up, and this is the help page that is created by that. So I started with these code comments. Fairly simple, except for just remembering these different directives like @param and so forth. And those become a slightly more complicated RDoc file. So we can see, for example, that we avoided having to have these names and usage and alias and title directives. We can just type those out as the first few lines of our code comments. These get turned into this LaTeX documentation, and then when you actually have the package loaded and the user wants to look up the help function, this is what they see. So that was documenting a function. Methods are documented fairly similarly to functions because, yes.
Is there a way to preview like what it looks like as you're going?
Not really. That would be nice, but not really, no. Okay, so methods are documented fairly similarly to functions because methods are essentially just specialized functions. So here we're documenting the normalize and normalize generic function and the normalize method for our ProDXB object. So the first part looks basically the same as we had before. We have the first few lines are title and description, followed by the description of the parameters, followed by what is returned. The difference here is that by default, whenever we document different R objects, those will by default become separate documentation pages. But with things like methods, we typically want most of those methods to either be on the same page as the generic function or on the same page as the class. Which way you do that is kind of up to you. So here we want both the normalized generic function and our normalized method to be documented on the same documentation help page. And so the way that we're doing that here is this @RDName directive. That's saying that we want both of these to be part of the same help page that we're calling this normalize. And so that means whenever I use this @RDName directive, whatever I'm documenting there will end up being documented on the same page as these. So here, this @RDName normalize means document this on the same page where this shows up. So here I'm just this is just the generic function which I want exported, and here's the method that I want exported. And I guess oops. Yeah, so I made a slight mistake here in that there's supposed to be an additional line here to document that it is in fact a method. So here we're also going to add the at method directive to say that this is a method for normalize and prot exp. And we can see I did do that correctly with these other methods that we have. So here we're saying this is going to be the method for summary, prot, exp, and so forth. And that, along with the, so this at method thing, that's also similar to the at export. That's often necessary to make sure the namespace is generated properly. So in this case, this not having this for me before was technically wrong because it means my namespace was not as correct as it could have been. So when documenting methods, we want to use this at method, then the name of the generic, and the name of the class. We also want to just document the package itself. So that if people just want to say, for example, if I load dplyr and I want to know what dplyr is about, I can get a help page for the package itself in general. The issue with that is that when writing that sort of documentation in roxygen 2, all of the roxygen 2 code comments have to actually be about some sort of R object. So if we want to document something that doesn't actually exist as an R object, then we can just document null. So here, I just have this null here to allow roxygen 2 to correctly find this information that is going to end up as the documentation help page for the package as a whole. So you can see the first few lines are the same as we had before. The first one is the title of the help page. Then we have a description of the help page, just describes what the package is doing. When documenting the package, we have this at doctype directive saying that it's a package. We have the name of this help page. In this case, I needed to do this to disambiguate the name of this help page from the name of the help page for the function prot_exp, because R itself is case sensitive, so it doesn't matter if I can have both prot_exp lowercase, prot_exp uppercase, and those are totally different things. But operating systems are not necessarily the same way. So a default macOS installation will be case insensitive in the file system. So that's why in this case I changed the name of this prot_exp to this help page to prot_exp-package to make sure it didn't keep overwriting it when it generated the help page for that function. Okay, and now the bulk of what I have here is actually directives that are going to end up deciding the namespace of this package. So here I'm importing from all of the packages that I want to use in this package. So here, for example, I'm importing the methods package because I use S4 classes, and so the S4 classes and methods are implemented in the methods package. I'm importing dplyr, I'm importing tidyr, and then for some packages, I'm only importing specific functions from them. So for example, here I'm only importing the median function from the stats package. I'm only importing the summary and plot generics from stats4. From the graphics package, I'm only getting box plot, and then I'm only getting certain things from the S4 vectors and summarized experiment packages. And oftentimes it's fine to just import the whole package, but there are situations where you want to just selectively choose which functions you need from that package. And I did actually run into that situation with this specific package, and that happens when you're trying to import from multiple packages that have functions or classes of the same name. So both stats and dplyr, as we saw before, they both have a function named filter. When we're working interactively in our global environment, that's fine. We have a search path that can decide which version of filter we find first, and we can disambiguate which one we want by typing dplyr : filter or stats : filter. With a package, we need to be a little bit more explicit. So we'll end up with some errors or warnings if we try to just import all of dplyr and import all of stats, because then we'll have two filter functions, and if we just type filter, how is our package going to know which filter function we need? So in general, there are times when it's a good idea to fully qualify your functions in a package. So say dplyr : filter, that's a good idea to do just so you know for yourself which filter function you're using. And then in addition to that, that's why I'm only getting the median function from the stats package. So whenever I use the filter function, it's the one from dplyr. And there's no way to get confused between the one from stats and the one from dplyr. So all of these directives will end up, these will be used to generate the namespace file for our package. And so this is where you put all of these for all of the packages that you're going to end up using in your package. Any questions on those, how that works? It can be a little confusing if you're not familiar with the concepts. So what that ends up looking like. So the namespace file itself is generated from the combination of these import directives and these export directives. And the way that all of these code comments for both the documentation and the namespace file are actually turned from the comments into the final form is either using roxygen 2, you can just use the roxygenize function, and that'll, you just give it the directory of your package, and that'll automatically generate all of the documentation from your code comments. Another way to do that, which is essentially doing the same thing, is you can just, if you just have DevTools, you can just use the DevTools document function, and that'll go and call roxygen 2's roxygenize function. Document just calls the roxygenize function, so there shouldn't be a huge difference in these, because they're both ultimately calling this roxygenize function. Document does a few extra things to like do some error checking. I'm not actually sure what it does additionally, but either of them will get you to the same place. So for example, let me go and delete all of my documentation here. I'll delete my namespace. And now, let's see, where am I? Okay, so now I can use this DevTools document function. I'll give it the package, and it'll generate all of that documentation for me. So now that documentation is back, and the namespace has been generated again as well. So a few more details on this namespace file. So this namespace file uses directives like import and export to specify which R objects you want to import from other packages and which to export to the users of your package. So namespace itself uses directives very similar to what is used in roxygen. So import just makes all of the functions in a package available to your package. Import from selectively imports functions to use from another package. Export exports any R objects such as functions for other users to use. And then if you have S3 and S4 classes and methods, those are handled slightly differently. So there's an S3 method directive that will export S3 methods, And then there's export classes and export methods directives that will export S4 classes and S4 methods. So what that ends up looking like for this package is we can see we have that what was generated was we have this S3 method directive for all of our S3 method functions. We can see now the normalize is properly there when I had forgotten to include it before. We're exporting all of the things we want to export and importing all of those things that we imported in those code comments as well. Now, if you happen to not use roxygen 2 or something like that, by default, like say you use package skeleton to create your package and then you just do everything by hand, the default namespace that it gives you is looks like this. So it's actually just using a regular expression to decide what to export. So if you just make a very, very simple package for yourself and just want to export everything, you could do something like that. This and this just exports everything. But typically it's a good idea to actually specify all of this explicitly. And again, in this case, we didn't write this by hand. It's all in the roxygen comments. The data subdirectory includes any data that you're going to end up using. They're saved in an RData file. So either using save or save RDS functions. They're compressed in some way. And when the package is loaded, this data isn't loaded automatically. Instead, they're loaded either when the user types their name or when they use this data function that loads them automatically. So any data sets that you include in a package must also be documented, just like the functions, methods, and classes, and so forth. So you can document those using roxygen as well. So for this prot.exp example, I included the twin example data set that we've been working with so far. And to document it, just like with documenting the package itself, where we just documented null, we do the same thing to document the any data sets. So here I just have a null so that I have some sort of R object that is associated with the code comments here. First couple lines are just the title and a description. Here I have some LaTeX code that's just giving me a list of the different columns in the data frame. An example of loading the data and the format. So just describing what they look like. So we have 2 data frames, and it gives the number of rows and columns for each. So you document data sets just like you document everything else. All right, any questions so far on the R subdirectory, man subdirectory, namespace, data, or how to document these things so far? Any questions, concerns, debates? Yes? It depends how much you've missed something and how grievous your error. If you're just trying to build and install the package, some errors will be bad enough that you're not actually able to build and install it, and some will still allow you to build and install the package, but will be caught by our command check. So that's the main purpose of, one of the main purposes of doing this R command check. We'll look at more of that in a little bit. So we want to be able to check everything in the package, make sure the documentation is all set up correctly and things like that. So there's a specific function that we can use to make sure everything is working properly. But it kind of depends. If you're just trying to install the package, some errors will be allowed and some things won't. So typically, there can be lots of times, at least with the documentation, you can have some errors in the documentation that just installing the package doesn't necessarily care about, but our command check will scream at you for. Okay, moving on, installed files. So the inst subdirectory, so any files in this subdirectory, I just move to the top level package subdirectory when it's installed. A few things this is useful for, so if you have any data that is not in an RData formatted file, this is the place to put them. So if you have like something that is in a CSV file and actually needs to stay in a CSV file, or some other format, maybe like a small SQLite database or something like that, that your package then needs access to. This is the subdirectory where you would put things like that. So, for example, the tidyverse has a package called readr that does things like it has slightly faster versions than the base R versions for things like reading CSV files and so forth. So to demonstrate that functionality, they of course have some CSV files provided with the package. Those need to stay as CSV files because you can't demonstrate reading a CSV file unless they're actually stored as a CSV file. And so these files would have been in that inst subdirectory in the source package. And then here in this readr package, they actually created a function that that finds them. And the way that you can do that on your own, you can just see the source of this function. So there's a function called system.file. And if you give it the argument package and just give it the name of the package, it'll find the directory of that installed package on your system. So, for example, let's see where my dplyr package is installed. So that gives me the directory of where my version of dplyr is currently installed. So if you need access to any files that were in that inst subdirectory after the package has been installed, you can access them programmatically using the system.file function. Let's see, if you have any additional documentation that isn't a vignette or regular R documentation, that could possibly end up here. And then also if you have any scripts for non-compiled languages that the package uses, so like Python, Ruby, things like that. So if your package relies on some sort of Python or Ruby or Perl script or whatever, those might end up in here. So conversely, the source subdirectory is specifically for compiled code. So you wouldn't put like Python code in here or anything like that. So the source subdirectory is specifically for C, C++, or Fortran compiled code that the package uses. And we'll talk a little bit in a bit how to call C++ code from R. Vignettes. So vignettes are typically R Markdown files that are compiled when the package is built. You can add a template for a vignette just using this DevTools function that sets up a template for a vignette. And so if you've seen R Markdown files, you've probably created one of your own by now, just as an example if you haven't done it before. So if you know how to write R Markdown, you know how to write a vignette. And it's typically a good idea to provide some sort of vignette when you're writing a package so people can have a walkthrough for how to use your package rather than just having to read documentation for individual functions. So for example, the ProEXP has a vignette, and you can view these vignettes by using the vignette function. I did not currently install it with the vignettes. This will end up taking a moment. So by default, DevTools. Oh. Looks like whatever documentation change I made, I might have broken something. So the vignette, what it looks like is an R Markdown document. Just looks like a regular R Markdown document, except the output is specifically as either an HTML or PDF vignette, and then there's some additional information that R will use about the vignettes here. So the vignette engine, by default, it uses Sweave, which is based on LaTeX. So if you want to use R Markdown instead, you specify the vignette engine, and then what the vignette will be, the name of it, and the index, the encoding. Most of this will be set up for you automatically by DevTools if you execute this. Let me try to fix this real quick. This is supposed to be like that, but for some reason it broke something. So we'll take a look at that in a moment when it's ready. Tests. So there's a unit test subdirectory. This is intended for unit tests. If you're not familiar with unit tests already, there are small reproducible snippets of code that confirm your code is actually doing what you're saying it's doing, what you want it to do. These are really important because sometimes you can go back and make a tiny change to a function. You think it does the same thing, but oops, it actually does something totally different. And you don't actually realize that until someone complains to you on your mailing list that you broke something. So unit tests are really important for helping you make sure that your functions are doing what they say they're doing. You can just rerun all of your unit tests to make sure things keep working after you make changes and that you didn't break anything. So we're going to use the test that package to help us write unit tests. So you can create a template for writing these unit tests with test that by just using this DevTools test that function. And that'll set up a template. And what that looks like is in the test subdirectory, there'll be one R script called test.that.r, and then another subdirectory that is called test that. The test.that.r one doesn't have much in it. It just says library test that and then library your package, and it runs test check, which is a function from test that. All of the actual tests are in this folder, and what those look like are like this. So using the test that package, you have this. You have all of these little functions called expect equal, expect is, expect equivalent, expect true, expect false. And these are all set up to test little assumptions that you make about different aspects of your code, different results that your code will return. So for example, here's as a sanity check, just making sure 1 + 1 = 2. And if for some reason there's something that isn't true, you'll get an error in these unit tests. So for example here, to test this package, we're loading the data set, making sure we can access them, and they're as we expect. Here I wrote a couple tests for testing the S3 methods and classes. So just making sure that this ProDXP object is actually inheriting from data frame, making sure I can normalize and summarize the data. Here, based on doing that calculation before, I just wrote down what I expect for this number, making sure that it is equal to that number. And when you do any sort of floating point comparisons in these unit tests, you generally want to include some sort of tolerance, since with computers you might have a 0.0000001 after this. So those numbers, you might get different, slightly different numbers on different systems, on different operating systems, when in fact they should be equivalent, but there's some small computer floating point error that means they're not. So we generally compare those kinds of numbers with a certain tolerance here. It's a kind of high tolerance, but it's fine. All right, let me see if that vignette is working. So here I have the vignette for this ProDXP example. So it's just a simple walkthrough showing what the package does, loading the data, running the methods on it, and so forth. Let's see. All right, so after you have all of this together, you want to actually build and install the package. So there's a few ways to do that. There's a few steps to take. One of the first ones is to actually build the package into a bundled package from the source package. You can use either the rcommand build command utility from the command line, or you can use the DevTools build function. And these will output that bundled package, so as a .tar.gz. So your package ends up as just a single compressed file, which is really easy to send to someone as an email attachment, assuming they trust you to not send them a virus or something like that. So for example, let's go ahead and build this ProDXP. So you can see it's checking the description, preparing it, making sure it's looking at the description, metadata information. When you build the package into a .tar.gz, it will actually also create the vignettes usually. That's not required, but it will typically happen. You can tell it not to build the vignettes if they're particularly time-consuming, just by setting vignettes equals false. And so the output of this is there should be a bundled version of the package now, and that's really easy to just send to someone if I don't have it on GitHub or something like that. All right, checking the package. So this is really important to make sure that there's no errors or incorrect documentation or things like that in the package. So it looks for common code errors, checks for documentation, checks the package can be loaded smoothly, runs all of the code in all of your examples and all of the unit tests. For CRAN and Bioconductor to accept the package, it must pass rcommand check without errors or warnings. That can sometimes be easy, sometimes time-consuming, depending on how complex your package is. Checking a package is best done on the bundled version of the package, since sometimes you can check a source package, but you might have some hidden temporary files in there that it'll throw warnings about. So like on a Mac, there'll be like invisible .dsstore files typically that are how Macs store information about your folder settings. So it'll complain about those, and those won't be in the bundled version of the package. So let's check this prot.exp package. I cleaned up most of the errors and warnings, but I didn't actually have time to clean up all of them. The main reason for that is the roxygen documentation for S4 classes and methods is still kind of confusing, and I have yet to find really good documentation for how to document those in roxygen 2. So at least for the time being, for my own packages, I've been writing anything for things that use S4. I've still been writing that by hand. For anything else, roxygen has been pretty easy and reliable, and probably I'm sure there's a way to get that working. But this will probably come up with a couple warnings about the S4 documentation. The issue is that it will complain for essentially anything that isn't documented, and it can sometimes be a little confusing how to link together the S4 documentation correctly. So here, I'm sorry?
Is it someone at Bioconductor that does all these checks before a package is uploaded to Bioconductor?
There's no person. There's computers. Yeah, they have scripts that run this manually every day for all of the packages on Mac, Windows, and Linux. So, for example, let's see. I go to Bioconductor. So all of the packages are built daily, so I can look at one of my packages, Cardinal. Right now it's only run on Linux and Windows. The Mac OS daily build is still running, I guess. So I can look at the check results on, say, Linux, and it'll tell me if there's any warnings or errors. The difficult part is if there's like warnings or errors on a platform that you don't actually have. So I don't actually currently have a Windows machine, so it can be sometimes tricky to troubleshoot any warnings I get on Windows. Hmm? Eventually, yes. So typically, for Bioconductor, it releases every 6 months or so, and you need to have at the very least you have to have no errors to be included in that release. I'm not 100% sure if they'll sometimes just skip over you for one release and then you'll be included in the next one or not. Depending on what the errors are, sometimes it's okay. Like every once in a while, one of their machines just breaks and everything has an error. So if that's the issue, then you're usually fine. But if you had a bunch of errors and warnings for a long time, they'll usually try to contact you, and then if you can't be contacted, then they'll put you on the deprecated list, and they'll eventually deprecate and remove your package then. All right, so here we can see all of the comments that rcommand check gave us here. So checks things like syntax, common syntax errors, make sure the description and namespace is filed, checks the documentation. We get some information about some undocumented things. We can note that Xinhen could have compressed the data much more, apparently. We run all of the tests and test that, and we end up with 3 warnings. So we have no errors, 3 warnings, and then we have some notes. Sometimes you'll get notes that are just tips on things that can be improved but aren't completely necessary. All right, so now that all of that is done, you want to install your package. There's a couple ways to do that. Once you have the bundled version, so a .tar.gz, which if you ever need to install if you ever get a .tar.gz, you can just install that from R using the install.packages function. You set repos equal to null, otherwise it'll go looking on CRAN. The type is equal to source, since it's still considered a source package, you're still installing it from source. So that's one way to install these. And conversely, you can use the DevTools install function, and that takes the source uncompressed package as its input. So here I had installed ProDXP earlier. So say if I restart here, I can start up ProDXP and I have those functions and stuff that we wrote and so forth. So that's a quick crash course on how to build a package. Any questions on that, on what we covered? Confusions, concerns? All right, so hopefully that was helpful. So that was how to build a package, and if you have any more questions on that, we can go back. And for now, we're going to move on to performance profiling and debugging our code. All right, let's start off with a fairly simple motivating example. Suppose you wanted to write a function in R for getting the mean of some sort of numeric vector, and you didn't know that the mean function exists in the stats package for some reason. Because, well, lots of programming languages don't have a built-in function for getting the mean of a vector. So why would R? Well, because R is designed for statistics. But suppose you didn't know that, so you write a function to get the mean of a vector. So here's a fairly straightforward way that you might do that. You have a vector x, you initialize a variable called sum to 0, and then you loop through every element of x and add the current element to that sum, and then you divide by the length of the vector. And that should hopefully get you the mean. So just to double check that. So my mean 1. So that works. So that's one simple way to write a mean function. Who can tell me a way to do it a little bit more easily? Still assuming we don't know that a mean function exists. Yes? Exactly. If we know the sum function exists, then we can at least just use that. We can just use the sum function and divide by the length of x. And we'll get the same answer. So the main thing that we've done here is we wrote a for loop that looped through every element of x. And here we were aware that there is some sort of vectorized function that already did that calculation for us. So now that we have those two versions of our mean, calculating the mean, they get us the exact same answer, but do they do it at the same speed? So there's a package called microbenchmark that we can use to find out. So here we're going to load up the microbenchmark package. And what the microbenchmark package does is it's designed to time little calculations. So if you have some sort of a small toy function that may be executed hundreds of thousands of times somewhere, then you can time that small function with microbenchmark and get a very precise estimate of how long that function will take to execute. And you can compare slightly different versions of that function to find out whether you're gaining more efficiency or you're making it slower or faster or whatever. And so microbenchmark, so how it does that is it will actually run the function many, many times. I think the default is 100 times. So it'll run the function 100 times and then give you a summary of how long it took for each of those 100 times. And so that's why microbenchmark is really designed for microbenchmarking, so these little functions. So you would not want to use this function for benchmarking something that takes 3 hours. It's really for comparing different small functions. So here, we're going to just create a vector of random numbers, one of 10,000 entries, and we're going to use microbenchmark to time R's built-in version of mean and R2 versions where we calculate the mean in a loop and with sum. Wow. Mm-hmm.
Yeah, it's on the drive.
Yeah, I posted it like last night, I think, or earlier today. I think it was last night. So if you downloaded everything at the very beginning, you'll need to go back and get this, but it should be on the Google Drive. Yeah, it should be right here. Performance profiling and debugging. All right, so here I'm getting the output from microbenchmark. It doesn't. I'm printing it manually so I can specify how many significant digits, just so it prints a little bit more compactly. You get the same information either way. So here we can see that mean, R's built-in mean function took about 26 microseconds on average. And for these sorts of timing things, we generally want to look at the median amount of time it took. The mean can sometimes be misleading because these timings can be very skewed. Sometimes your computer is doing something else and there's just one timing that went way too long or something like that. So the median is much more robust to those sorts of outliers. So we typically look at the median for these. So here it looks like the R's built-in mean function took about 26 microseconds. Our version that used a for loop took about 341 microseconds. And then our version that uses sum takes about 10 microseconds. So first thing we see is that the version that uses the for loop is much, much, much slower. And then one thing we notice is that our version that just uses sum is actually about slightly more than twice as fast as R's built-in mean function. The reason for that one is just that R's built-in mean function also does things like handling NAs and missing values and infinities and things like that. So it does a few more things than R's, which will not necessarily handle those as gracefully. But in general, we can see that the for loop in this example takes much longer.
Is there a reason in that example you had to set up a distribution of 10,000 values but don't look at 100?
Yeah, so the x vector is length 10,000. Is this what you were looking at?
So it's looking at all 10,000 values 100 times.
So I'm getting the mean of a length 10,000 vector.
Right.
And microbenchmark is going to run this function 100 times. Yeah. So it's running it 100 times so we can get an idea of how long this function takes to run on average, because it'll take a slightly different amount of time to run each time.
Yeah.
All right. So that was one simple example, and in this example, you would be kind of wise to follow the advice of don't write for loops in R, which is not necessarily the true, but in this case it was. All right, so let's look at another example. So, question: can someone volunteer to describe what this function is doing? What is this function doing? Any ideas? Exactly. So it goes through. So X here is a matrix, and it loops through each column of the matrix X and counts the number of NAs, the number of missing values in each column. So here, X is a matrix. we're creating a variable called call_nas, which starts off as a length 0 numeric vector. We're going to loop through each of the columns of x, and in each iteration, we're going to create a variable called num_na started at 0, then loop through each of the rows of the matrix, check whether each individual element in that column vector is an NA, whether it's missing or not, and if it is, we're going to add 1 to this num_na variable and assign it back to itself. After we're done looping through that, the rows of that column vector, we're going to append this num_na to the existing call_nas numeric vector, which gives a total, keeps a running count of the number of NAs in each column. So let's make a data set where we can do that. So here we're just going to generate a data set where we can count the number of NAs in each column. So now we just have a matrix of random numbers, and randomly every once in a while we have some missing values. And let's see how long this particular function takes. So this function went pretty quickly. Took about 2 milliseconds for this to run. But now suppose we suspect that we can probably do better than this. So suppose we have to end up running this function many, many times, and it ends up being the bottleneck of our code and slowing us down a little bit, and we want to write a faster version. So how can we speed up this function? So R provides a built-in profiling utility called rprof. Rprof works by sampling at specific intervals and checking what function is currently being called. So that means we can use rprof to understand which functions are taking up the most time in execution. One thing to understand about this is rprof is sampling at specific intervals. So if your function executes very, very quickly, then you need to change the intervals at which rprof is measuring. Otherwise, you're not going to get enough sample data. Because rprof is doing sampling, and you want a large sample size, right? So you need to make sure you actually sample enough times to get enough data to figure out the profile of your function and what is taking up time. So that means this version with this data set took about 1.7 or 2 milliseconds. That's not very long. So we're going to make a larger data set just so it takes longer to run this function. So here we're making a larger version of that matrix. And now we're going to profile it with this rprof utility. So rprof, just calling the function on its own, turns on R's profiling mechanism. We can change the interval of how often it is sampled using the interval function. So I'm going to say I want to sample this every 0.01 seconds. I think that's in seconds. Yeah, in seconds. I am going to run the function itself on this larger data set, and then to stop the profiling, we just run rprof null. The reason for that is usually the first argument to rprof would just be a file name where this sample data gets placed. By default, it'll just create it in a file in your current working directory, and giving it null turns it off. Who can guess why? Who knows what this invisible function does? Let's see. So here I have a vector 1 through 10. If I wrap it in invisible. So invisible just invisible just turns off print. So typically, whenever we type something at the command line, hit enter, it'll get printed. And invisible just turns off that printing. So when I'm counting the NAs here, or in general when I'm trying to time a function, why might be a good idea to turn that off? Why might it be a good idea to do this? Yeah, it takes time to print things, and I don't really care how long it takes to print the result. I want to time how long it takes to actually get to the result. So it can often be a good idea to shut off printing things here. So that's why I'm doing that here. I don't care how long it takes to print. All right, so now there's a function called summary rprof that will tell me how long it took in various functions. And that output looks like this. So here I've run this function. Rprof has sampled at various times, and it ended up with this distribution. So we spent about 48 or about 57% of the time just in the function itself. About 27% of the time we were doing is NA. About 14% of the time we were doing this C concatenate combine vectors function, and then about 1.19% of the time this all function was being evaluated. So the main takeaway in terms of how to interpret this is ignoring the function itself, because that's the only thing we're running. It seems like this is NA function is taking up most of the amount of time inside the call NA's function. So if we want to improve the efficiency of this function, one place is to look at where is NA is being called and how often that function might be being called. So let's go back and take a look here. So here is NA is inside of these double loops, and is NA is being applied to every single element of this matrix. But if we know about is NA, there's no reason to apply it to every single element of that column, because is NA itself is already vectorized. So we can apply just is NA to just the column itself as a whole. There's no reason to loop through the entire column and check each element individually. So one simple way to improve that is we can just do is NA on the whole column itself. We take advantage of the knowledge that summing up a logical vector gives us the number of trues. So here sum is NA will give us the number of missing values, and then we'll append those and return the results. So this should be a slight improvement. We should be spending less time in is NA because we're taking advantage of the fact that it's already vectorized. First things first, we want to run them both versions of our functions and make sure they're actually returning the same thing, kind of a mini example of a unit test. And now we're actually going to time them and see how long they take. It looks like this second version is significantly faster than the version where we were checking each individual element of the matrix. So now, can we do better? So we're going to run rprof again, see if there's anything else that can be improved, and we find out that the next thing that is taking the most amount of time is this C function. So C is just our simple function for concatenating vectors together. If we take a look at where that is being used in our code, you can see that at each iteration of this loop, we're concatenating this new number, that's the number of missing values in a particular column, with all of the ones that came before. So this C function, it appears, is taking the most amount of time now. Why might that be? So one thing, kind of a side note, we've actually already talked about this a little bit, is understanding why this concatenation function is taking up so much time. It helps to understand a little bit on how R actually treats its objects when they're being modified. We've talked a bit before about how R treats objects as immutable, so you can't actually change R objects themselves. So you should probably already know the answer to this. But when we create a vector x and assign into it, say here the fifth element, the question is, what actually happens to x? There's two possibilities. Either x is modified in place, or R can create a copy and modify the copy. And which of these two possibilities usually happens? The second one usually happens. Does the first one ever happen? The first one actually does happen sometimes. So the answer is it actually depends. Oftentimes we'll end up with the second case, and usually R will copy x and modify it. But there are times when x is actually modified in place. And understanding when and how that happens can end up saving you a lot of time in terms of saving memory and saving and improving speed. Because if you know that x is always going to be modified in place and not copied, then your function is going to be much, much faster than if it gets copied every time. So if we understand how and why R decides which to do, when to do which, we can take advantage of that. So here we're going to use a package called tryr that lets us take a little bit of a look into R's internals. The issue with this package is it doesn't really play well with RStudio. All of the functions in it will evaluate, but they will give you the wrong answers. And that's because, so here basically RStudio, so the issue with this is RStudio has this nice little environment browser that lets us see what variables are in our global environment and so forth. It's very convenient and very nice. The problem is that means that there's always going to be a reference to all of the objects in our global environment, and that will affect how often objects get copied. So in a sense, there are occasions when RStudio is going to make your code run slower, actually. That will not always happen, especially if it's inside of a function or inside of a package. But there can be times when that will happen. It's usually not actually a thing to worry about. It's not a reason to stop using RStudio because all of these are just things in the global environment. If they're inside of a function, inside of a package, it won't affect those. But since, for the sake of examples, it's easiest to look at things in the global environment, if you run these functions in RStudio, you will get the wrong answers. So here, we're just going to create a vector x. And we're going to use this address and refs function from tryr to take a look at these. So address just gives the actual address in memory of where this object is being stored. And then refs is an internal thing stored but for all our objects in a slightly complicated C struct. And refs is typically going to be 0, 1, or 2. Refs, in this case, here is 1. That's because we've assigned a vector to x, and there is one variable called x that is referring to the actual object stored in this location. Here we're going to assign x to a new variable y. If we look at the refs again, we can see that the address is the same, so both x and y are currently pointing at the actual same location in memory. They're pointing to the exact same object. No copies have been made. But this refs attribute that is only typically visible inside the C code underbelly of R's interpreter has been incremented to 2. And that's because now we have two variables, both x and y, that are both referring to this actual vector in memory somewhere. Refs will be 0 if there's no variables referring to something. It will never be more than 2. So R actually only tracks whether there is 0, 1, or more than 1 references being made to an object. So this isn't actual reference counting. It's just checking whether more than 1 variables have ever referred to an object. And so what ends up happening here is, let's take a look here. We're assigning this vector to x. We're assigning that to y. And if we look at the address of x and y, right now they're at the same location in memory. If we try to assign something in to the 5th element of x, and then look at the address of both of these in memory, now one of them is different. So we can see y, we didn't change y, so y is still at the same location in memory, it's still pointing to the same object, whereas x, we tried to modify x, but there's now another variable pointing to the object that x referred to, so that means R is now going to make a copy of x and modify that copy. So the idea here is, since here we since there's a second variable that has been referred that is pointing to the same object in memory, now the object is going to get copied. If we want to take a closer look at that, there's a function built into R called traceMem. It just prints a message every time the traced object is copied. So here we'll create a vector x again. We can start tracing the memory on it. So we just call this function traceMem on x. It prints out where it's located in memory. Now if we assign something into it at this point, nothing happens. And that's because at this point, x is still being modified in place. So right now, since there's only one variable pointing to this object in memory, it's actually being modified in place. Now we're going to assign x to y, so now both x and y are pointing to the same location in memory for the same object. And now if we assign something into the 5th element of x again, now we're going to get a message from traceMem that says this object has been copied to a new location in memory, because now both x and y are referred to the same object. One of them is being modified, so we're going to make a copy and modify the copy. And so what that means is that if we have only one variable that's referring to a vector, and we have that entire vector existing in place beforehand, we can actually go ahead and modify the individual elements of that vector, and those modifications will actually happen in place without copying any memory. And so what that means is we can get rid of that concatenation function, and if we just initialize this call inat vector to be the same length of the number of columns of x, here we're assigning into it the number of missing values of each column. So typically we might think that each time we assign into it, oh, maybe that object is going to get copied and we're going to use a lot of memory or something. But because there's only one actual variable that's referring to this, this is actually going to be modified in place. If we created a second variable that referred to the same thing, that would be a huge issue, and then we would have a lot of things being copied. But because we're handling it like this, this is all just going to be modified in place and happen really quickly. And to prove that, let's take a look at the timing. So here in this third version, we don't save a huge amount of time. It turns out that concatenation wasn't being a huge issue. That's still a fairly small vector, so copying it didn't take much time. But we did gain about 30 microseconds, and it is actually being modified in place rather than being copied. So that seems like a good place to stop now and break for lunch. We'll come back and continue with the rest of this talking about performance and scalability in R.